This is the third video in this tutorial series on producing a Zynq-based instrument doing signal processing on the FPGA. In the first video we talked about how to set up the Coheron SDK and how with just a few text files we could edit those to define our instrument. And then in the second video we went into detail the design of the logic part which was going to perform the DSP function that we require for this tutorial, which is a software-defined radio. In this third video we're going to pull everything together and so run the big make file and then see it running on the target hardware. Now, before we go ahead and run the make file in anger, there's just a few more files that it's worth looking at in the SDR instrument directory. Now, we'd copied across this pulse.hpp file, which are the C++ drivers that are going to run on the ARM of the target board, and there's some Python libraries and programs that we're going to use as well. So let's have a look at what we had in the pulse.hpp, which is borrowed from the pulse generator program, and this has a bunch of stuff to do with generating pulses, and we're going to edit that and come up with something that's going to look more like this, which has reference to the registers that we want to set, the receive frequency and the volume and so on. So these are the functions that allow us to set the volume, so load the register value on the FPGA and receive frequency, and to be able to read back status values. The FIFO stuff we've kept the same as it was for Pulse HPP. The FIFO stuff's just the same, most of it. And then there's a Python library which allows us to access those functions from a Python client program running on the client machine, which then will connect to the Red Pitaya over the network. We're now ready to build our instrument using the make file to put together all the files that we've just been editing. We need to pull up our terminal. We need to make sure we're in the right directory where the Coheron SDK resides. We then need to make sure we've sourced the settings. And so we're now ready to run our big makefile command, which is this one here, make config equals instrument, the path to the config.yml file, and then we're going to just build it all together. So we go ahead. Now this will take quite a long while, and so we'll just skip through this and put it on pause and then rejoin it at the end. Okay, so now it's done its stuff and it's generated this zip file which could be sent directly over to the Red Pitaya or the target board, assuming we've already got a system up and running on an SD card, or if we're wanting to create a system from scratch, then the next step is to generate the SD card image. The next thing is to generate the OS with this command. Okay, we'd already run it earlier, so that's very quick. And so in our temp SDR directory we have the OS, and then next to create the image we need to run this sudo, so that's the command there. Again, this could take quite a while, so we'll just skip forwards. Okay, so sometime later we have our image file now in the SDR directory here, and we can flash that onto the SD card using whatever software you might have available. But you can do that in Linux using the dd command. Now, once we've copied the image onto the SD card and put the SD card in the slot here on the Red Pitaya, you see in the image at the top left, then we're ready to go. A quicker way might be to download the image, the stock image from the Coheron site, and then we can copy directly the .zip file that was created here direct onto the target board over the network, and that's much quicker to do. So when you're doing future edits of your design, then you just simply copy that file over using the host command. So that looks like this, okay, and that assumes you know the IP address of the board. Now to get that, I've got the board here on my desk, so locally from my PC I can run nslookup, and of the name of the device, which is Coheron 1, I'd change the name. By default it comes in as Coheron, and then that gives us the IP address here, so we'll pick up that IP address here, and then using this command we can send it directly, and that very quickly copies it onto the board. Now you'll notice that we have some LEDs flashing there, indicating the signal level being picked up. Now that will depend on what frequency we have the receiver set to, so that's the next stage, is to run a Python program to configure the device. So we see the RF input coming in here from an antenna that we built just here. Now the antennas uses some ribbon cable, which is constructed using some IDC connectors here. This is 10-way 10-strand ribbon cable, and we've separated 9 ways off onto one side of this connector and 9 on the other, but staggered so that we have 10 turns in total, and so the extreme ends of the ribbon taken out to this SMA connector here. In parallel with the loop we have a trimmer and some polystyrene capacitors, and that comes a few hundred picofarads. So with the 60 picofarads of adjustability here, we can tune to whatever receiving frequency we want. We're going to try and pick up radio 5, which is at 909 kHz, and so we can pick that up in the AM band. So what we need to do is to run the Python program. So we'll just remind you what the Python program looked like for this device. So that was this program here. We're going to call the driver set frequency command, put in our 909 kHz, and we're going to set the volume, in this case to 9, but you're going to have to adjust that by trial and error. And then we're going to plot the signal. We're going to plot the two signals that we're covering off the logic, the signal going to the speaker and the signal after the AGC, but just of the I component. Okay, so let's have a look at what that looks like. Okay, now this is the baseline subtract taking a while to act and bring it down to 0. And the speaker signal here, and this is the spectrum. Now if we look at the LEDs now, they're pretty well fully lit up. One of the reasons for that is that we're getting a lot of noise from our USB input signal, which we're just taking from a simple mains supply, which is actually putting in a lot of noise. So we'll have to replace that with a battery device. So to do tests, we'll use something like this, which will give a lot more stable 5 volts. But anyway, already we're seeing some signal here, and we can now go and do some tests. We'll connect onto the data channel, that's this one here, a headset to listen to the demodulated signal. Okay, so it's all wired up now. We've got this loop aerial connected to the input ADC. Loop just held on this bit of foam to hold it out, and taking the output from the DAC here up to the headset. You can hear this noise if I just bring this up to the microphone. And you can see the difference in signal strength as we adjust the aerial position. We can see the signal going down and up, measuring the signal level. Okay, and then when it's correctly oriented, we get the best signal.
What she did is she turned up in Newcastle Airport.
Okay.